Hello, everyone. Thank you for joining us for today's State of the Field series. My name is John Patinos. I'm a project manager at the C2 Smart Center, a US DOT designated Tier 1 University Transportation Research Center. In the State of the Field series, we're aiming generally to bridge the gap between the best of research and the state of practice. And today, we're joined by Terry Tamutis. We're going to share the latest advances, opportunities, research bottlenecks, and what perspectives and skills are needed from the workforce of tomorrow. Quick notes before we begin. We'll be recording this session and uploading it to the C2 Smart Center YouTube channel. I want to encourage you to participate in this webinar through posting questions one of two ways. You can use the Q&A function at the bottom of your screen, and I'll read your question to the presenter at the last 15 minutes or so of today's events. Or you can raise your hand and I'll call on you and allow you to unmute your microphone. So I'm going to turn it over to Professor Hani Nassif. He's the Associate Director for Technology Transfer at the C2 Smart Center. Hani, why don't you take it away?
Thank you, John. I thank you for accommodating this seminar, and I want to thank C2 Smart for their initiative to do this series of seminars on structural health monitoring. As you know, one of the themes of the center is the infrastructure resilience, and and structural health monitoring has been one of our major themes, and we invited many speakers in the past. Today's speaker is Terry Tamutis. He's not a stranger to this field. I've known Terry for more than 25 years, I would say, and he's been a top expert in the acoustic monitoring, as well as the fiber optic monitoring. And not to my surprise, we've had a couple of collaborative efforts, and we successfully applied the state-of-the-art fiber optic sensing through his company. His company is Structural Monitoring Solutions. He's the president. He's by training, he's a mechanical engineer with more than 30 years of experience, and is very well known worldwide with many projects. So without any further ado, I'd like to start the seminar. Go ahead, Terry.
Thank you very much. Thank you for that great introduction. Just want to talk about some of my past experiences and case studies. A little bit about acoustic monitoring. It's a field all unto itself. It's much different from strain measurements. I'll talk something about just a little bit about suspension cables, since there's a lot of these in the New York City area, and then repair cost and return on investments, and then best practices that have been set up over the past 10 years for using structural health monitoring. And then there's a Hawaii project that we did in 2020 and the BQE, Brooklyn Queens Expressway, and the Roosevelt, which I'm actually down on site now in a hotel room. But I'll be back on site doing some final work on this bridge that I'll talk about later on. But just my personal structural health monitoring experience, and I try to highlight some of the New York City area, the Brooklyn Queens Expressway, which I mentioned, a Niagara River Bridge up in Buffalo. There was work with WSP on this. It was using acoustic emission monitoring on a pin that had a problem. Ogdensburg Bridge, and then in 2016, actually did some initial work with acoustic emission on the GWB, and then other bridges, go back to 2001 on the Ben Franklin Bridge. That was for the suspension cable, where there were issues there. But I've also written, text or chapters in books for AS&T. Wrote a section for bridge testing, doing mostly what I'm talking about today, but this is available. It's a great resource for grad students. It was written for grad students that are interested in acoustic emission. So this will be published very shortly. But acoustic emission is a unique science. It's the physics of how sound travels and materials. And what we'll just talk about briefly today is how much energy comes from an event, how quickly it rises up, the duration of that, and then location. Those are some of the key parameters that we use for most of what I'll be talking about today, which is wire break detection in bridges. Again, structural health monitoring is very specialized. Even if you're a structural engineer and you design steel bridges, you typically don't cross over into concrete bridges. If you're a strain gauge expert, you typically don't, and use electrical strain gauges. It's a new learning process to become an expert in the fiber optic side of strain gauge measurements. So using different people for different applications is critical. So I work with PhDs in strain gauge technology using brilliant techniques, and then others that use Fabry-Perot sensors. So each of those people or PhDs are experts in specific fields, and then the interrogators are a whole nother side of the story. So you don't go to a heart surgeon for brain surgery and vice versa. So much like we're doing here, you don't go to, you know, somebody that designs a bridge to do structural health monitoring. It just doesn't work. So the acoustic emission sensor that we're using is much different from the other types. The older types of acoustic emission sensors use a piezoelectric crystal in there. And then when you tap that sensor with any mechanical input, it converts that mechanical energy into electrical energy. And that electrical energy goes back to a system, an acoustic emission system. Going through copper cable, you have resistance, you have problems getting that tiny voltage has to be amplified and sent back to the system. With this fiber optic system, what we're using is when we detect a wire break or a crack in a material, that signal travels through the tendon or suspension cable or cable stay. And what happens is it vibrates a mirror inside the transducer. The mirror is very sensitive. It's a cantilevered mirror. What it does is it reflects the laser back to the system differently. So there's a laser that's pulsing 5,000 times per second, and it reflects off the main mirror and then off of the vibrating mirror. And that standing wave between those two mirrors is highly, highly accurate and sensitive when it detects something. So it could be used for vibration detection, seismic detection. We're using higher frequency sensors. So the sensor placed in New Jersey could actually hear an earthquake in California if we're using the lower frequency version of this. The other thing we can do is we have, you know, fiber optic cable that leads up to these sensors. These sensors could be, their cables could be up to 3 miles long because it's a laser. It doesn't attenuate through the fiber. As you know, there's underground or undersea fiber optic cables that transmit for hundreds or thousands of miles. And it's a very robust system. The sensor is also very robust. So even though it's a very accurate mirror inside, we've done submersion testing. We've done pull tests on the cables. Even though it's a fiber, tiny glass fiber in this cable, it's taken, you know, essentially 26 pounds is 3 bags of sugar, that much force on the cable before anything happened to it. That gold block there is actually the sensor itself. And then we've actually done vibration testing on this. Since we put this on a rail bridge, we wanted to make sure that this would last for 20 years because the project we're doing in Hawaii is a 20-year project. And if we had to go back and replace all the sensors in 15 or even 20 years, that would not be a good thing. So what we found from this doing 2G test, which is twice the amount of vibration that you get from the rail bridge, it was done for 70 days or 640 million cycles, which comes out to hundreds of years. If you do the train calculations, how many trains per day, how many axles on the train, et cetera. Long story short, it'll last a long time. So the sensor is very reliable. We estimate this will last well over 50 years. If we're using an electrical sensor, inside of there is a preamplifier. Those preamplifiers, no matter how well you waterproof these, I used to make these sensors, they still leak. Water and moisture will get in there, they'll short out. The other issue that you have is the connections with the cable. So no matter what you do, these things eventually will short out over time. Where the fiber optics, we don't have that problem. We have a one cable system. So on the top, we have an electrical based system. Each cable, each sensor needs a home run cable. So you have to do wires all the way back to the box. And these wires for acoustic emission can only go about 300 meters, and that's dependent on the frequency. So that's using a very low frequency sensor. But here with the fiber optics, we can go up to 3 miles. We can put 4 sensors onto one fiber. These fibers are a little thicker than the human hair, and we can, attach 4 sensors on there because these are at different frequencies. For the laser pulses at different frequencies, it's a spread spectrum laser. So each sensor on that fiber is tuned to a different frequency. So this is an example of a bridge where they were getting 1 to 2 wire breaks per day. It's a big bridge. You can see, the condition of the tendons and how concerned they were with this bridge. But long story short, the electrical sensors, this was done in 2010, and the technology back then, there was these fiber optic sensors weren't around. Using electrical based sensors, you have to have high installation costs. You can see the wire racks there. They had 800 electrical sensor cables because they had 800 sensors. So with the fiber optics, we could do 6 fiber optic cables instead of for the 600 acoustic sensors, and 1 cable for the 200 other types of sensors, because strain gauges, LVDTs, temperature cable, or thermocouples, we could put on, up to about 20 to 40 of these sensors on 1 fiber. So as I mentioned before, we're using 1 system. It's light, it's a laser. So essentially the vibration temperature sensors, these are all coded, and the system knows, you program that code or that sensor number into the system, and it knows it's a displacement sensor, it knows it's a vibration sensor, it knows that it's an acoustic emission system. If we had to use, different types of electrical sensors, we would need multiple types of boxes, because strain gauges work off of vibration, displacement works off of voltage, vibration works off of charge amps. So the acoustic emission works off of AC signal and the DC signal. So we need 3 different types of electrical boxes, where the laser system, the interrogator, doesn't care. It's just light. We're also using, I'll talk about distributed fiber optic strain gauges. We're using this on the BQ Brooklyn Queens Expressway, as well as the Roosevelt. So this is a guy from NASA. They've been working with this. It's been around in the aerospace for 20 or more years. But the yellow cable that they have there is a distributed fiber optic strain cable, where there's 1,400 sensor measurements that you could get off of that cable. And where the white cables are electrical based sensors, and there's only 18 there. So you can imagine if you're doing a large project like the Roosevelt or the BQE, to wire up a bridge like this would require a lot of cabling. So this is a new innovation too. So this is the strain cable that we're actually using, but this is about the diameter of your pinky, and inside of there are 3 different metal tubes. So that yellow jacketed has a metal tube, and the red jacket has a metal tube inside of it. And then that silver tube is actually a temperature sensor. So there's 3 fibers in there. There's redundancy, 2 extra. So those float freely in an oil. And then the strain fibers are actually in the red and the yellow tube. And those are adhered to that blue jacket. So any force, just a tiny bit of force on that strain cable will let the laser know that it reflects back to the system differently. So the graph on the bottom, the blue graph, is actually the strain measurement. And then the graph on the right, the temperature, is the flat line there is the temperature. So what happens is that the blue line, which is on the bottom here, the laser goes out, it takes measurements every 4 inches. It goes back to a splice box where the temperature and the strain fibers are spliced together. And then the laser returns on the temperature fiber. So if it nulls out the temperature difference over that fiber. And just a quick case study that I did back in 2010, this was with another company. These were I-bars. There were 384 of these fracture critical I-bars in the Bay Bridge and in San Francisco. And one of the engineers from Caltrans was walking down the bridge. He looked up, he saw this 14-inch crack. This was like a holy crap moment. But you can imagine, this is fracture critical. So essentially they went out, they needed this bridge to last because they were replacing that bridge with the one on the left, the new San Francisco Glen Bay Bridge, self-anchored suspension cable bridge. But Caltrans put out a bid. They invited the top 10 structural health monitoring companies, 8 of them bid. And this was awarded to an acoustic emission company. So the acoustic emission system worked well. It actually found the problem where this 1.5-inch electrical conduit was rubbing up against the I-bar. It lost an 1/8 inch of material. If it had gone a little further, another eighth of an inch, they would have had to shut the bridge down, according to the structural engineers. And if it had happened in the head of the eye-bar, the round part of the eye-bar, they would have had to shut the bridge down right away. The original crack was caused because of this 8-inch dimple that was left over from the forging process. So this bridge was inspected every night with JLGs, dye penetrant, or ultrasonics. They were using all different types of inspection mechanisms. And right on the deck level, and it was inspected for 18 months before the acoustic emission system found this. The acoustic emission system was only on for a couple of weeks, and it detected this pipe wear. And it was a big deal because it was 9 o'clock in the morning. It was rush hour in San Francisco. So to close a lane down takes an act of God. But sure enough, for $40, Caltrans went out to Home Depot and they got some pipe insulation and they fixed the problem. So it was a great success story. This is another application with NASA. So this just goes to show specialty. So this is a large building where they monitor, or where they assemble the solid rocket boosters, the white rockets on the side of the space shuttle. These are brought in on the rail car, they're lifted, they're rotated, and they're stacked on top of each other. In 2007, I went there to give a presentation to NASA engineers and 3 scientists that were sitting in the back of the room. Turns out the 3 scientists went away. They tried to develop their own microphone-based system, acoustic system, after I gave that presentation. This was a safety critical concern. They spent $3 million, 3 years, and they couldn't come up with a solution. 2010, they called me back. I went in there. I told them these are where we're going to place the sensors to find this big bang that was coming from this building, because every time the bang was so loud that the assembly workers inside didn't know where it was coming from. They said it wasn't the overhead crane because they had lasers on there that were monitoring the movement of the crane. It turns out it was the overhead crane. They were stick slips. So the wheels in the front of the crane wore out because this was around since the Apollo days. So essentially the Big Bang was found with the acoustic monitoring. They solved the problem. But I'll talk a little bit more about wire breaks now on bridges. So with pre-stressed post-tension adjacent box beam girders, this was a 45-year-old bridge in Pennsylvania near Pittsburgh. And they just had another collapse there. This was rated 4 out of 10. It was inspected 2 months before the collapse, and this broke under dead load, and it came down right in front of a woman in a minivan on Christmas Eve. She was going a little bit faster, it would have been a different story. But she ran in it, still ran into it, but fortunately nothing happened. But the same thing happened with a post-tension or pre-stressed box beam in Canada too. So the inspectors were called out there. They said it was okay, and the police insisted that they come out. They wanted to push the inspection off, but 2 hours after they inspected, this came down and killed 5 people. But the Woodrow Wilson Bridge, and there's 34 other bridges out there, they have Sika chloride contamination. So this Sika route had elevated chloride levels in it. What VDOT and Maryland State Highway Administration were really worried about were the putty grout, not so much the chloride contamination, because this grout was known to putty very easily. What Michael Sprinkles at VDOT said is, if you add just a little extra water, and he was mixing it in the lab, it would putty. So imagine pouring this on a large production level with semi-skilled workers. But this was a large project which took 30 acoustic emission systems on it. And New York State has also used acoustic emission. Srinivas Alampali, he and the district, the region, I think it was Region 12, got this near Syracuse. But they were having issues with it. They put in supplemental tendons, but the beams here were monitored with acoustic emission. And VDOT has done a good deal of work. They have about 4 bridges now with acoustic emission monitoring on it. Michael Sprinkles is the contact there. But they've done a lot of research where they were finding shrinkage on the grout and would get voids, and this would cause corrosion and tendon failures in the bridge. They tried vacuum grounding, they tried corrosion inhibitors, but it just didn't seem to work over the years. And finally, they just, instead of spending all this money and adding more and more to it, They just decided to monitor. And when they hear wire breaks, they go out, they do an inspection, then they do mitigation or replacement of the tendons. And they also did this on 2 other bridges called the Lord Delaware and the Eltham Bridge. But these other bridges had new high strength concrete. They were relatively new bridges. And this was the last tendon failure. It was a transverse tendon on the Varinon-Enon Bridge. So this is a cable stay bridge. That's one of VDOT's few, but the acoustic system, this was their recommendation to do that because inspection just didn't give them enough results. They couldn't get to the areas where the main concern was because they were in anchorages. But South Carolina has issues with this on the Waldo River Bridge. They did kind of the same thing NASA did. They put a microfilm-based system in there, and they're only listening for tendon failures, not wire breaks in the individual tendons. But there's a large Volvo plant and a Boeing plant that are just on the other side of this bridge. So when this bridge goes down for an inspection, they have issues. So they lost one tendon. They replaced the tendon. They inspected all the other tendons, and 3 months after the inspection, they had a second tendon that failed. Like VDOT said, inspection doesn't work. So that's why they went with monitoring. But this is out west on a bridge that I'm working on with an engineering firm. I was their subject matter expert on this project. But these were supplemental tendons that were put in on this bridge. And of course, the one in Italy, these were wire breaks inside the stays. But California's having this on the wire break failures, tendon failures on the new high-speed rail that they're putting out. And even Hong Kong and Normandy, France, and other places in the UK are having major issues with post-tension wire break. But this was same thing VDOT mentioned, is there was shrinkage. So these, the end of the tendons were opened and, just corroded over the years. So you can see the air pocket. That this report is online, but you can see the air pocket in there where they were having corrosion issues. So this is a project where we installed acoustic monitoring on a Hawaii rail bridge. So they had 3 tendon failures and they had 13 replacements. There's a lot of political issues going on with this, with budgets and things like that, and delays. But you can see the elevated rail bridge, and it goes for 20 miles. We're monitoring 6.3 miles of this. And essentially, before we took this project on, we wanted to make sure that this technology would work. This was the first ever application of doing this. So, with all my years of training, what we did is we went out there, we placed 2 sensors. We took spring-loaded center punch. It's just a mechanical device that gives a pop into the concrete and simulates a wire break. But we located these wire breaks or simulated wire breaks very accurately and caught every one of these with a sensor spacing of 70 feet. So you can see the gold blocks on top, and then the blue dots are actually where we did the center punches every 10 feet. But the other issue was this was a rail bridge, and acoustic emission listens for sound. So we needed to be able to filter out the train source. So we went to Atlanta. I got in the bucket truck. We mounted 2 sensors. We waited for a train to go over, and the train was going a little under 50 miles an hour. And we used the spring-loaded center punch. And this is the data from the system. This is unfiltered. So you can see the red indication, and the green behind that and the blue behind that is the train signal. So the sensors caught the train signal as well as the center punches, but you can see the center punches are there, but behind that signal. So again, before we put this in Hawaii and took on a 20-year monitoring contract, we wanted to make sure we could filter that out. So on the right-hand side is a beautiful graph of an excellent signal to noise ratio. So you can see the spring-loaded center punches, and way down at that baseline, you can see the train noise has been so well filtered out. So that allowed me to take on this contract and do the installation and know that we'd be good for 20 years. I wouldn't have to go out there, replace sensors or fiber optic cables or laser interrogators every 5 years, 10 years, because that would just bankrupt the company. So this technology has to last. It's bonded. So this is a balanced cantilever. It's over H1, which is the main highway in Hawaii. There's a lot of rush hour traffic under there, so they were concerned about this, any issues of tendon failures, this would be a problem. But there's 26 sensors in the balanced cantilever, and we're measuring the interior tendons, not the exterior tendons. And you can see the sensor that's mounted there. And then there's 61 span by spans that we're actually monitoring over a 6.2 mile distance. So these were selected because of the grout was put in, several weeks late, or maybe months, I forget what it was. But these specific spans, we ran fiber to it. You could see up in this corner here that there's a basket, and that's filled with fiber optic cables that run the train and the control systems. So there's no electrical cables inside of the bridge. It's all fiber optics because the train arcs, it creates an interference with any radio signals and things like that. So fiber optics is immune to that. So that's why they chose fiber optics for the controlling system. So laying an additional cable in there was very easy. So the way we set these up on the span by span, we put these on the deviator blocks. So if anything happens on any of these tendons, and one of these sensors is actually redundant, we can tell, if a wire break does occur, if it's the left side or the right side, or here, the top or bottom set of tendons. But it's easy to detect, if something goes wrong. This is the system. It's relatively small. There's 3 of these systems. This one, I think, is monitoring about 4.5 miles of track over the spans. And these are actually wire break signals. I won't say if they're from the bridge itself, but these are true wire break signals. And you can hear the short, sharp burst. So as I mentioned before in the early slides where we're looking at rise time, we're looking at how fast the signal jumps up. And then there's this beautiful taper off of the signal. When this happens in a span by span on an exterior tendon, we get like a reflection back here. So we get like a small echo back here, which tells me it's in an exterior tendon. But repair cost, the DOTs are paying a lot of money to have repair costs done, like Seattle DOT, South Carolina. So by detecting these early on, you could, like VDOT's doing, they could tell where to do the mitigation and the inspection and actually save money in the long run. The bridge we're working on now, the Roosevelt Bridge, has to last another 50 years. It's only 20 years old. But what FDOT said is that this will eliminate the hunting and pecking, which I'll go into a little bit later on. But it's also, structural health monitoring is also part of best practices. So FHWA has put out, manuals on this, NCHRP 534. This is for suspension cables. But this has been around since 2001, and it's still a great document in terms of acoustic emission. But if you have indications of things going wrong, this is level 3 or level 4 corrosion on wires. It's using acoustic monitoring is very important. But I'll talk about something in a little bit later on. But TRB just put out this recent circular. This is made for owners because this was put together by experts in the different fields, strain gauge, fiber optics, acoustic emission, etc. It talks about the limitations. It talks about which technology to use in which situation. But this is a good resource for owners. But one of the most important things in there is that don't over-instrument a bridge or sensor a bridge. It talks about progressive diagnostics. So if we find something on the Roosevelt Bridge, we put in the minimum number of acoustic sensors as possible. And if we detect something, we could add another system. We could add more sensors. The fiber's there. The fiber's cheap. To do about 8 miles of fiber in those bridges was only about $12,000. It was very inexpensive. And the labor's there. So we might as well take advantage of that to add, 2 extra cables as backup should we need them. But the instrumentation and the sensors are the expensive part of it. So we did the very bare minimum much like you go to a doctor and he puts a stethoscope on your heart, and if your heart's okay, you go home. If not, he sends you to the cardiologist. The cardiologist sends you to get an MRI. They put you on stress tests. So that's when you add more sensors. So we're just doing progressive diagnostics, but for best practices too, the acoustic monitoring has been credited for, saving the Hammersmith, for finding indications and where to strengthen the bridge. But for suspension cables, this new sensor that we're using, we could use a one cable system, and it's a low profile sensor. So it's right next to the cable clamps. But the problem with running, cables, coax cables to electrical sensors is you just kind of get a mess after a while. And again, there's bound to be issues with shorting and whatnot on the cables. So it's the fiber optics is a much nicer solution, elegant solution. But AECOM has written articles on this. This is done by Barry Colford. He was the bridge master for Forth Bridge in Scotland. He used it there. And so he's very familiar with it. Now he works at AECOM, but he wrote a great article on this. We also have a white paper on this that explains the return on investment. But essentially, if you're going to do opening and wedging, it's best to monitor 6 months to a year before you do that to find out where the broken wires are. And that's where you send people to go in and do opening and wedging. Short story, Ben Franklin Bridge, wide layer went in, Sante Como, they opened up 3 panels on the Ben Franklin Bridge. They got enough money to open a 4th panel. That 4th panel had 10% of the wires broken. And that was a major issue. So they got money to open up every panel, 330 panels on that bridge. That one panel out of 330, the probability of detecting 1 out of 330 or, using 4 over 330 is, a fraction of a percent. And that's what NCHRP 534 says, is that if you open up a few panels, the probability of detecting broken wires is less than 1%. But this white paper explains that and the return on investment and going to the right locations. But, wire break detection is being used by TxDOT, VDOT, New York State. It's been used in the UK. And for suspension cable bridges, it's being used a lot. For the Brooklyn-Queens Expressway, we're using fiber optics. It's one of the best choices for this. So other types of sensors have been used on this, but what they're worried about is, the spans on this. So using electrical gauges, you would have to, wire up. You would have to power the boxes first of all, and there's no power out there. So running power lines would be difficult. And then installing these boxes, these would have to be serviced, and then you would have to run individual lines to the sensors that are measuring strain or issues with the spans, any crack openings. So somebody from Parsons told me that you should think of these as piano keys, since this is a cantilever structure, that these are 50-foot, wide piano keys. And if one of them is weak, that would flex downwards and the strain gauge would pick that up. But you can see this would cost, a lot of time to install, a lot of disruption. With the fiber optic system, we would just use one cable. We would measure down to 1 microstrain sensitivity every 4 inches, and we can run over 10 miles of fiber optic cable. So when we did a small project with this, with BQE, this was in a small room that actually had power. So we didn't have to run any power lines. We just ran the fiber from the system to the spans that we were monitoring. And the results of the measurements were very accurate. So at Rutgers, they implanted this blue cable into this beam, and then they cut a tendon, and then they estimated their theoretical calculation of a loss of tendon would create about 79 microstrain difference. The strain gauge picked up 80 microstrain difference, and the string cable picked up 80 microstrain. So they were, right on top of each other, very accurate. This is a blind test. too, but they've also done other testing. So Rutgers students went out and actually installed this on the BQE, and they did a fantastic job. They learned a lot, I'm sure. And the cable was, we designed the cable in certain ways, which I won't go into, but this was also implanted into the deck by New York City DOT. They dug the trench for this, and then the Rutgers students actually laid this in there along with point strain gauges too. You could talk to Dr. Nassif about the results of this, but just wanted to thank the grad students from Rutgers. They took their masks and their hard hats off temporarily, very quickly to get this picture, but they were religious about wearing hard hats and PPEs on this job. But also thank you to New York City DOT, C2 Smart, for this contract and hosting this, but also the joint venture. And then the last part I want to talk about, this is a project I'm down in Florida now working on. This is a Roosevelt Bridge. These are two bridges side by side, a northbound, southbound. Each is 4,500 feet long. The bridge is only 2,600 or 26 years old. So the story is that they inspected the south side of the bridge, and then next day they went to the north side of the bridge. And the next day, somebody calls up and says, you should come out and check the bridge because there's this huge crack in it. So either inspection missed this crack or it happened within 24 hours. Either way, it's a scary situation. But I've been talking to Florida DOT for over 10 years, telling, this is a problem, this is a problem. All these problems are taking place all over the world with post-tension bridges. Be active. And so they let me come back in and give another presentation. And I suggested that they use a strain cable and the acoustic emission sensors. So the acoustic emission sensors will tell them what happens in the future. The strain cable will tell them what happened in the past. And if we get indications from the acoustic sensors of wire breaks taking place, it'll tell us how much strength we have left in that bridge. And essentially, there's segment joints. I put some blue lines in this top slab to show, just exaggerate the segment joints, but you can see all the way back, the segment joints are very clear, and these run in the floor as well, or the bottom slab, obviously, as well. And you can see these blue lines. So the strain system is measuring strain every 4 inches. So if there is an opening in any of these segment joints, with 1 microstrain sensitivity, we'll be able to detect, I forget what HDR said, like, I don't know, 0.0 something cracks, an inch crack on it. It was a very fine crack. But these are the systems that are installed on the bridge now. So this, the bottom box here is just a backup power supply, UPS for the acoustic monitoring system. This is considered the primary system, and then the secondary systems, which are actually just as critical as the UPS, as the AE system, are the strain systems here. So one box is the CPU, one is the fiber optic interrogator. This black cable here is actually connected to is just a protective tube. So the blue cable is implanted in the concrete, and it's epoxied in place. So it's now it's integral to the concrete bottom and top slabs as we mounted this, throughout the bridge. But this is the acoustic sensor and the AE systems. And then this is actually a blind test. So I sat in a car underneath the bridge while somebody from an engineering firm called Cardno went inside, and they used the spring-loaded center punch, and they did center punches in specific spans. And I didn't know which out of the 20 spans he was doing. But yeah, we detected him, no problem. And I, did screenshots and text them to the engineer that was doing this. But also the same was true with the strain cable. So what they did is they went out and they heated the cable. We can't stress the cable. And this shows the cable without the epoxy on top of it, just so you can get some clarity on how it runs throughout the spans. But I believe right about here is where it makes the transition. It goes up the web wall and it goes onto the top slab and then goes all the way back to the anchorage. but this also passed the verification test. And our contractor score too is 96%. So it was, August through January, essentially. We have excellent scores of 96%. It would have been, perfect if we had a DBE, but it's really hard to find tradespeople and even DBEs in this day and age down in Florida. But these are the strain cables. There's essentially 4 miles of this that we used. It goes on one side of the bridge, the other side of the bridge on the bottom slabs, and it makes a transition to the top slabs. But we're measuring strain and temperature every 4 inches. We're getting about 66,000 strain measurements per hour for 9,000 feet of bridge. And then this measures dynamic and strain. And thanks to Dr. Nassif suggesting this, we found a way to do the dynamic measurement as well. So this is monitoring in real time. So it's not just taking a strain measurement passively every hour. It's monitoring, several times a second. And if a large truck comes over the bridge and causes a strain to, go above a certain threshold, it'll buffer the before signal, like 15 seconds before and 30 seconds after, and we can expand those or decrease those. But it's a beautiful system now, and working with structural engineers and people who are experts in this field, we can add these different features, but this will give off real-time alarms. And this, essentially is a lower cost than putting in electrical strain systems. I believe the original RFP or request was for only a couple hundred strain gauges, but here we're giving them 66,000 strain measurement points. And it's all threshold, and we're telling them exactly what segment, a joint segment, is opening up. So this could be, perfect for like applications like the PQE and other bridges, where you need to take a lot of measurements, but you need it to be automated. So we're providing actionable data. We're not just handing somebody a report and say, here, look at the strain measurements every month or every quarter. So it's by doing this, we're able to, define the true impact of the repairs that were done on the Roosevelt, because there were other sections that were reinforced or had supplemental tendons added to this. But, we can do different modeling with this, working with, like Dr. Nassif and other experts in this field. But, we were on time and on budget with this project. And somebody from HDR, one of their structural health monitoring experts, they were the designer, quote unquote. I was really the designer of the system. And then I was the contractor, the person that went and installed it. But I told them exactly what systems to use, how to place the sensors. They did more of the structural side of this. But they said that this was one of the best and easiest projects that they've ever worked on. They were really surprised. But we have experts in, with 20 and 45 years in acoustic emission, NDT, and, structural engineering. So, these projects are long-term, so we're not going anywhere, 20 years and 5 years for Florida DOT, but we're always looking for new technologies to complement the existing technologies that we have today, or other companies make a box. They're tooled for making that box. They'll keep on making that box until the company goes away. And that's pretty much where the state of electrical sensors are right now. For small projects, electrical sensors are still very good. For larger long-term projects, fiber optics are the way to go. And I've worked with electrical-based sensors for 25 years. I thought that was the be-all, end-all, but this new technology, fiber optics, has really opened my eyes. And were there any questions?
Thank you, Terry.
Hey,
it's great. Go ahead, John.
I was going to say, if the presentation component is reaching its end, I would open it up formally to the audience for questions. They're not come in now, but yeah, please feel free to use the Q&A button at the bottom of the screen, and we'll ask some questions to Terry and to Hani about the research that they presented today. I have a question in the meantime, Terry, and maybe even Hani. I just wanted to use this opportunity to ask for more details on what comes next for the structural health monitoring systems that you've been setting up on the BQE, where C2 Smart has a test bed. So what's the latest and what's going next?
Yeah, for that one, let me, the BQE has been really a great opportunity, and I want to acknowledge the involvement of our partners, the joint venture, Parsons and ACOM were involved in helping us out a lot. And the New York City DOT, they really took it on themselves to give us the chance to work with them and think out of the box. And I think what Terry has mentioned and has shown, it has been a great experience for me personally and my students to learn more about this fiber optic. And, we kind of probably mastered what Terry, had, and we worked with them closely. And I think it's the answer. I think what Terry said is correct. This is I don't want to say it's a new generation of structural health monitoring, but it is a new way of doing continuous monitoring, especially when, for example, in concrete structures, you wouldn't be able to predict where the crack is going to form if there's to be any crack. And thus you need a continuous system that can detect the intensity and the location of such an event. And, putting, point sensors everywhere is helpful, but is not the right answer. And I think in BQE, that was a very, very good example, having it, 70-year-old concrete structure, although it's, and it looks, many locations, there are some probably corrosion things, but, if you want to detect any extreme event, you need to have such a fiber optic system. So for the task on that one, that was a pilot study to figure out what kind of equipment, what kind of sensors, and now we're working closely with New York City DOT and the joint venture to put up to imagine or put a concept on how would the future instrumentation of such a structure would look like. But we have enough data and enough experience now to be able to put that together. And I think, soon we will be able to, we're working closely now with the joint venture, Parsons and their team, to be able to finalize that. So the BQE has a WIM also. I want to mention also we have a weight in motion data collection. So we are from the load side, we know what's going on. And from the resistance side, we're trying harder to use the state-of-the-art technologies, and point sensors and distributed sensors like the fiber optic that Terry has suggested. And by the way, this fiber optic is different than any other sensors I've worked with before. It's more rugged, and I can see it. We work with it in the lab. I think it is great to put it into new structures because that's the way in the future. They're very cheap. It doesn't cost a lot, the fiber itself, and you can put miles and miles as Terry presented. So I would suggest, even in a new structure, to put something like that, because you could use it for the next 20 years to be able to maintain or get more knowledge about the system. Terry, you want to say anything about?
I agree. And even if you can't leave the instrument behind because it's expensive cost, the cable is relatively inexpensive. So you can implant that in a structure, take a reading today, come back in 2 years, take another reading in conjunction with a load test. So that's what one major DOT is looking at right now, is doing that, because they have a lot of bridges they're uncertain about. And, I'm always looking for the lowest cost method to do things like this. So just a temporary or a system on site, but the permanent cable, and some systems you have to be careful because they'll lose the strain measurement. So if the power dies or something like that, much like an electrical based system, you'll lose the offsets and things. So this technology is great for even doing, all bridges essentially.
We have a looks like Eric Yermak wants to raise his hand and ask you two questions. So I'm gonna unmute you right now, Eric. You should be able to unmute yourself and ask directly. Yep, go ahead.
First, I want to say thank you for bringing this presentation to us, Dr. Nassif. And Terry, you and I have been trading emails back and forth for a little while now, and I'm really glad to have this opportunity to see your presentation. It was a great presentation, and I was just thinking that this is the kind of system that could probably very economically be deployed in new complex structures and just build it in as a bid item, that you would deploy a system like this. It seems like, and we would go with sort of that minimalist approach that you could expand out. I really liked the kinds of things that you were saying. I've also done some of this work myself and know the challenges of powering a bridge. And you're showing a technology that doesn't really require the same types of power that conventional sensors might require. And I also liked the durability and robustness of the system. That when you say not affected by moisture and humidity, these are huge advantages that you can operate this over a long period of time. And so I see that there are some really great applications for this, and we'll keep our eyes open for opportunities in the future. This is more of a statement and a thank you than a question.
Thanks.
Thank you, Eric.
I should say, yeah, we welcome statements as well, especially if they're kind ones like that, Eric. Yeah. Thank you.
Thank you, Eric. It's exactly what, when Terry and I were thinking about the BQE, that's exactly, I think it fitted exactly what you mentioned. And for that reason, I think, our recommendation is to really use this system, especially on situations where complex structure or a structure where it is sensitive to type of unusual loads and stuff like that, especially when they're aging also. Thank you, Eric.
So, Terry, you're mentioning this collaboration that you've had with C2 Smart and with RIME. I was curious to just hear your thoughts as a practitioner. In your view, where are research consortiums like C2 Smart best positioned to contribute to improving our infrastructure resilience? Maybe like what research areas or bottlenecks would you want to see more time spent on?
Well, there's a lot of unique structure, unique problems. I think a lot of the larger engineering firms don't know about this, even though they have somewhat some expertise with it in-house. But I've worked with a lot of universities across the country when I was, with another company, and they would just, buy a small system, put it in the lab, and that's where it would stay. There's only been maybe 3 or 4 professors out there like Hani that have actually gotten it out in the field on a real structure, taking real measurements instead of just bending beams. When he did this at Rutgers, he was testing the technology, vetting it to make sure it did work for the BQE, because he's putting a stamp on that, and it was right on. The measurements were right on what the other sensors said. So research is great, but field research is better. So
yeah, we like that too. I think we got real data, but I think you didn't show that, Terry, but we had a very big lab component to validate this system, and we did precessed concrete beams with cracking, and I wish I could you could have borrowed some of the results, but I don't think the time was there. But yeah, this was definitely one of the most rugged system I've used. I've used fiber optic sensing, and the concern was always the fiber being damaged under field conditions. This type of fiber, and it's unique to your company, I know. It's not only one fiber; it's the 3 fibers embedded inside a metal cover, and then on top of the metal cover, there's also a plastic shielding. So it will shield it, and my students work with it. They splice it. This is the good thing about it. You could have your own splicing in the field. It's not simple in the beginning, but all my students now, they know how to do it. Very simple, and it was allowed us to go longer and longer. So yeah, I think the main thing I talk about that because that's really the future, in my opinion, and I think we want to breed civil engineering students that know this kind of technology now, because it's needed, and that's the way to go. I've been involved in in the conventional type of strain gauging. That will not go away, but I think for this kind of applications, especially in segmental bridges, in concerns on the, the embedded tendons where you don't have a quick way of finding out, the acoustic part is also as valuable in my opinion. So I would suggest for segmental, for post-tensioning, for even pre-tensioned structures, especially aging ones, you will need to have a system like that in the future.
So we have, unless someone wants to sneak in one last question in the last 4 minutes, I just want to begin to thank Terry and to thank Professor Hani Nassif for sharing this great presentation with us today. We're really excited to see what happens next in your field. And we're definitely very excited to see what happens next in the BQE testbed. If you, audience members, if you enjoyed this this webinar, and if you want to learn more about our existing efforts in infrastructure resiliency and the structural health monitoring setup we're working on to deploy on the BQE, definitely check out our website. It's C2 Smart. And if you enjoyed this webinar, definitely follow us on Twitter and LinkedIn and join our mailing list. We're going to have a couple more of these state of the fields, and we'd love to have you there and to ask your questions.